Alright, anyway, I was thinking about that lensing stuff. It is kind of an interesting subject. Um, lenses, we're always looking at a different portion of somebody. Like if you walk away from somebody, see, the idea is even when somebody's 60 feet away from me, they're still the same height. So like if we were all in space, everything's producing the same amount of light as it was before in our change in perceptions. You see, it sort of relates to that whole time dilation thing because it's all about this perception thing. Is only because we're absorbing a certain different percentage of them. And the real trick is with this whole lensing thing, it's about the size of the lens and the size of the thing you're looking at. What light you're actually, what part of the thing you're seeing, and whether the light is converging or diverging. And so it gets kind of complicated. And I was thinking there might be one thin chance for lensing, but it just doesn't seem very reasonable that it would happen that way. But anyway, and it would have to be with objects much closer, not far away. But yeah, so like if something's the real trick is so if you're looking across at something and they're the same height, these lines are all parallel. You know, the light can come off of here parallel. But the truth is there's light going at all these angles. And the thing that's happening is when you look at something, you know, your eye is tiny, okay, the tiny thing, and what it's really doing is just taking a percentage of the light, and you know the percentage that's coming off at angles. So it's it's not parallel. It's it actually is converging into your eye, so to speak, and then being reprojected on the back of your retina. So there are sharp angles, and the lens is dealing with the sharp angles of your perception. But if I move the thing back further, it's a completely different photons now that you're collecting. There still might be a couple that are parallel, but the angles will change, and so it's actually a different photon or area of the person, so to speak, or whatever you're looking at, that you're actually seeing. So every time something's moving, you're really seeing different places on the thing. A different little piece of its surface that's reflecting the light at the right angle for you to see it. So you're not really seeing the same thing, as funny as that is. But the really funny thing I thought about it was that everything's so much brighter than we're actually seeing it, because so much of the light coming off of everything we're not seeing. It doesn't go into our eye, so there's a huge amount of light coming off of everything. When you think about it, just huge. I mean, I haven't really thought about what the percentage would be, but I mean it's a ton. What percentage of the light emitted by a surface that's I can see in this dimension. So the stuff obviously going in the other dimensions wouldn't count, but the stuff in the dimension I'm looking in, what percentage of the photons coming off of that thing actually are going to my eye. That'd be interesting, if somebody knows that kind of statistic, it'd be interesting to know what percentage of the photons I'm actually collecting in this little eye. So I was thinking about the lens, and just the fact that what you need is to have a circumstance where you need to do the inverse of a regular lens, which is you need the outside part to bend less, kind of a thing. And what size the things would have to be. Because the real problem is we know that it's a bigger lens we're looking into when it's gravitational lensing. So we know the lens is huge by comparison to the eye. So we know the angles coming off the lens are huge. Even though the thing is far away, I'm just saying that the angles are big. They're not insignificant angles. Let's put it that way. Because the thing in real life is big. You can't change the fact that the thing in the lens in real life is really big, and our eye is really tiny in real life. You know what I mean? Not the delusion of space making a difference. Because I guess what I'm saying is distance doesn't really make a difference. It just changes how many photons you're getting and from what angle they're coming at you. And so obviously when the big thing is close, the only way to see it is it's sharp angles, because it's really high and really low. So those are really sharp angles. So the further away it goes, the angles get less sharp, but they're still converging to my eye, because my eye is always going to be smaller than the thing. There's never going to be a circumstance where the thing isn't going to have to, make light come up to my eye because it's so far away. Now that's the tricky part. See, the thing is bigger than we are. Yeah. So does it ever get small enough where we're actually looking at light coming off of it off of it this way? And that wouldn't be possible, right? So even if we're over here, the thing is bigger than us. So there's no way for the light we're looking at to be coming at an angle like this from it, even if it goes really far away. I mean an angle going out this way. I mean it can never diverge and get to our eye. Light that's diverging off of this thing couldn't possibly get to us. Because no matter how far away it goes. Because there's a reason. Yeah, because the angles would never add up. It could never get to us. So we have to be looking at light converging, even though it seems like it has to be light diverging. Yeah, so that's the question. All right, so so this light has to be coming, even though this thing's far away. The light coming, so if there's a lens in between it, the light coming off of this has to be converging. And so even if I make it further away, really far away, the light's still got to be converging onto. There's no way to draw it without drawing it wrong, because in a sense, distance is screwing it up. So I'm just trying to think. So if the light is actually converging, so if I just leave it with this, we still can't. You still got to deal with this fact, right? So this is what I thought of: is that if it was a weird angle, so this is the lens, and you had the object down here, and it was size comparable to the lens, so it was almost half the size, or pretty big. Then you could figure that the light coming from this bottom piece could be going, let's see, was it parallel? Yeah, I think it was parallel. Yeah. So this angle would be the sharper angle, the lower angle, and then to get to us. And this angle would be the less sharp angle to bend it to us. And so in that sense, so if the object was off, if the lens was picking up light from not behind the lens, from uneven behind the lens. So you were seeing, if you saw the lensing over here, it meant the object was in the opposite side of the lens. It's an object that has to be of significant size. And yeah, I'm just trying to think of what the angles are going to be at a distance. So what I'm arguing is that still wouldn't work at a distance, because there wouldn't be enough of a difference in the angles. The angles would get so small that the amount of gravity degrade would be still too significant. But at least you would have the right order for the bigger and lesser angle. So the stronger reflection would be of the bottom, needs the stronger reflection, and the top of the object, the photons there, need the less reflection. So in that sense, it could lens, the gravity lens would have the right weighting. So if it's an object, and the more, well, let's see, the more you bend it off the center of the lens, I wonder how big a difference that would make, because that would increase the angles a little. But yeah, it's not going to help you any. The angles are always going to be a little bit of a problem. But yeah, so if I go with it dead center, well, that's the way to do it. Okay. All right. Sorry. All right. So here's what I was thinking. I mean, I hate that this might actually work, but you know, it's the way it works. So let's say this light goes parallel. Oh, that's the strong gravity again. No, this one has to be parallel. It really gets confusing. Alright, so this one going to, yeah, so yeah, none of them can be running parallel. I'm just trying to think if you mix parallel light with converging light. So the parallel light would go, yeah, so so it's still, then it's going to get bent too much. So then I have to move it somewhere else. Okay, let's move it. Okay, sorry. Yeah, making a video while I'm thinking about it is probably not a great idea. Alright, so this is it. Alright, so this is the light that's going parallel. It gets bent more. So let's put the eyeball here. And this is the light going from the edge, and it has to get bent less. So there, that would work. But it has to stay, this big thing has to be big. Yeah, it has to be big. Yeah. So it has to be off center from the lens. So the whole idea of it something being exactly behind the lens, I don't think that would work. But unless it's really monstrous. Alright, we'll have to work on this. So at least this in theory, so if it said this could go through very weak gravity, and this needs strong gravity to get bent to here. So that would make sense. So you have to maintain those proportions. See, and that's the problem. Maintaining those proportions with what they're suggesting, which is, so what they're lensing is a big object really close. That might work. Something really big right behind the lens, but it's not light years away. Because if it was light years away, then this angle's going to get screwed up. It's not going to be straight anymore. You're going to need that. The further away you put it, the more you need to bend this one, and there's just not enough bend to bend it. The more parallel it's going to get. Okay. Well, anyway. So something from the center up might be able to lens, but I still don't think it's gonna. I still don't think the inverse square law thing is going to be overcome. Yeah. Well, more thought required. You still have to. The lens is bigger than we are. It's still a problem. It still has to get the light to us. So, yeah, it still ain't going to work. You're still not going to be able to have a thick piece of anything. Because the difference is too dramatic in too small a portion of the lens. See, if it was really big, then you can sort of understand. Because then you could get into the low gravity and be in the straight line gravity. But yeah, so it'd have to be huge. It has to be something huge and close. Or something really huge and far. But it would have, it'd have to be like half the size of the universe or something. Something really monstrously big. Yeah. So if it's something far away, it can't be a galaxy being lensed by of something bigger than it. It has to be. You have to be lensing something bigger than the lens A lot bigger. If it's going to be far away. Alright, well, I'll have to think on that one. But that's the only hope for the scrap. The fact that there's any hope is irritating. Okay, anyway, I'll think on it.